Here's example 5 with integration by parts. So this is another definite integral. So we did one of those a couple of videos ago, so let's do another one. So we want to evaluate the integral from -1 to 1 of x times the inverse tangent of x dx. Okay. So before we get started with anything else with integration by parts, is there something we can do to simplify this? So remember that rule? It's sort of a calculus 1 thing that's talked about. Well, it could be calc 1 or a calc 2 thing depending on where you are. But if you integrate an even function, okay, an even function, f of x dx, from -a to a, okay, then remember if you integrate an even function, then that's going to be 2 times the integral from 0 to a of f of x dx. Okay? So that's if f of x is even. Okay. So what does it mean to be an even function? Remember, if f of -x equals f of x for every x in the domain of f, then f of x is an even function. So we talked about even functions in a separate video. It's kind of a pre-calculus thing. And also this rule here is sort of, it's an earlier integration topic. So we could use this to simplify it. So x is an odd function. The inverse tangent of x is also an odd function. If you multiply 2 odd functions together, you're going to get an even function. Okay? So then we can rewrite this integral as 2 times the integral from 0 to 1, okay, of the exact same function, okay, of x times arctan of x dx. Okay? Okay. Now, if you're thinking, well, hey, there's no way I'd remember that, or I didn't really know about that, definitely keep this rule in mind. It'll be discussed in more detail in a separate video. But if you don't know this rule, it's totally fine. You could still evaluate this integral exactly the same way like this. It's just it's just a tiny bit more algebra to do in the end. But the steps until then are exactly the same. So we're just going to use the same integration by parts formula. So whether we do this integral directly or if we use this rule here to simplify to get this, it's the exact same thing. But I just want to point out that definitely keep stuff like this in mind because they will help you. Rules like this will help you simplify integrals and make them a little bit easier to evaluate. So remember, x is odd, arctangent of x is also odd. Multiply 2 odd functions, you get an even function. And then we can apply this rule here. Okay? So let's go ahead and evaluate this integral here. So before that, well, okay, let's toss the 2 inside of the integral. Okay? Or well, let's not yet. So I want to do that. It's going to make it easier. How do we know that? It's hard to say ahead of time, but let's, before we get that far, let's start choosing u. So remember, if we want to integrate by parts, we have to choose a u, okay? So if we choose a u, go to our Liate, or whatever, rule. So remember, choose u to be the first type of function that appears on this list if you go from top to bottom. So what kind of functions do we have? X, that's algebraic, okay? And arctan of x, that's inverse trig, okay? That's the inverse tangent function. So inverse trig appears first, it's right above algebraic. So we choose u to be the arctan function, okay? So we can rewrite this integral then as the integral of, so now I want to toss in the 2, so the integral from 0 to 1 of, let's say, arctan of x times 2x dx, okay? Now, why did I do it like that? Well, first of all, why did I rewrite it? Well, because now it's easier to point out what dv is. Okay? So if u is the arctan of x, okay, remember we just chose u to be the arctan of x because that's what this Liate rule tells us to do. Okay, choose u to be the inverse trig function because it appears above algebraic and that's all we have, inverse trig and algebraic. So choose u to be this, and then dv is forced to be everything else. Okay? So dv is forced to be everything else, including the dx. So let's come over here and write that. So u equals arctan of x. Okay, u is the arctan of x. So then dv is forced to be everything else. Okay. So if you're wondering why did I toss the 2 into there, well, this is why. So if dv is 2x dx, then what's v? Well, we integrate dv to get v. So if we integrate 2x dx, what are we going to get? We're going to get x squared, right? And yeah, technically there's a plus c, but remember for integration by parts we don't have the arbitrary constant on the v. Okay, so just keep that in mind. So this is why I tossed the 2 into there, because it makes it easier. What if you didn't really think about that ahead of time? What if you didn't really know? What if you just missed it? That's totally fine, of course. Or what if you just did this integral? then, well, if we did this integral, we still choose u and v to be, or we still choose u to be the exact same thing, right? We just wouldn't have a 2 on here. But if you don't have the 2, this will just be 1/2 x squared instead, which is totally fine. Okay, it just makes it a little tiny bit more complicated later on, but there's really absolutely nothing wrong with that. Okay, I just want to point out, again, keep rules like this in mind. If you integrate an even function from negative number to positive that same number, you can double the integral and integrate from 0 to that number, okay, the same function. All right, and then here, since we tack the 2 onto the dv, that makes v a little bit simpler. So just some little tiny tricks to keep in mind. So definitely think about stuff like that. And do it wherever you can find it and see it. But if you don't see that, that's totally fine. So u, okay, when we chose u, that doesn't depend on the limits. So whether the limits are 0 and 1 or negative 1 and 1, choose u to be whatever function appears higher up on this list. Okay. All right. So continuing, if u is the arctan of x, then du is 1 over x squared plus 1 dx. Okay. So now let's go ahead and toss everything together. So we're going to use this formula now. So remember, when we do integration by parts with a definite integral, so this is the integral we're doing here, or yeah, this is the integral right here that we're doing with integration by parts. Okay, so this one right here. Now when we do integration by parts with a definite integral, remember it's the integral from a to b of u dv equals uv evaluated from a to b minus the integral from a to b of v du. Okay? So here we're integrating from 0 to 1. Okay, so we're just going to do uv from evaluated from 0 to 1 minus the integral of v du evaluated from 0 to 1. Okay, so it's the exact same formula as up here, just with limits of integration. So we did talk about that in the other video where we did a definite integral with integration by parts. So let's continue here then. So now the integral from 0 to 1 of arctan of x times 2x dx equals uv, so that's arctan of x. Okay. Let's get rid of this here. Arctan of x times x squared evaluated from 0 to 1, okay, minus the integral from 0 to 1 of v du. V is x squared, du is 1 over x squared plus 1 dx, so this is a v times du. Okay. Okay, so let's go ahead and work with this now. Now, if we want to evaluate from 0 to 1, okay, so again, if you didn't remember this, or if you didn't know this rule here, you'd just be evaluating from negative 1 to 1. So the only difference would be, if you did that route instead, you'd have a 1/2 here, you'd evaluate from negative 1 to 1. So it'd be exactly the same thing, just with different numbers. So it'd be just a tiny bit more complicated. And also, this integral would have a 1/2 in it, and you'd be evaluating from negative 1 to 1. Okay, but again, let's continue like this. So this is going to be inverse tangent of 1, so arctan of 1 times 1 squared minus arctan of 0, arctan of 0 times 0 squared, okay? And then minus, so evaluate at the top, minus evaluate at the bottom. Okay, so now this minus the integral from 0 to 1 of x squared on top divided by x squared plus 1, and then dx. Okay. Okay, so let's simplify this stuff over here. What is the inverse tangent of 1? So in other words, the tangent of what is 1? Okay, well, it's the inverse tangent of 1 is pi over 4. So that's a trig thing. Okay, so we don't want to get too hung up on that in this video, but inverse tangent of 1 is pi over 4. 1 squared is 1 multiplied by 1, you're not really doing anything, so that's pi over 4. Inverse tangent of 0 is 0. 0 squared is 0, so you're just multiplying zeros together. So this whole thing is just 0. Okay, this whole thing right here is just 0, so it's, forget about it, it's done. And then what do we have going on over here? Okay, well, this is minus the integral from 0 to 1 of, okay, here, there's a couple different ways to approach this. So x squared divided by x squared plus 1, what we want to do here is we can divide this and do a technique called partial fractions, which we haven't really talked about yet. It's actually, I don't know if that would even work for something like this, but this is a little bit simpler. Or actually, what we could do is polynomial long division, or there's a nice little shortcut for ones like this. So what do we have on top? X squared, on the bottom is x squared plus 1. So what I want to do is stick a plus 1 on the top, but since I did that, I also have to subtract 1 on the top to make it okay. Okay. So what did I just do here? I just added 0. 1 minus 1 is 0. I just added 0 in a way that's useful to me. Okay? How is that useful to me? Well, now what I can do is split this up into two integrals. So x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. So let me split this up into two integrals. So that's x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1, and then dx on everything. Okay? Okay, so again, x squared over x squared plus 1. Since it's x squared plus 1 on bottom and just x squared on top, I'm going to add 1 and then subtract 1, and then that lets me split it up like this. Okay, so now I can split this up into two fractions, because I have x squared plus 1 and then minus 1. So I can split this up into two fractions like that. X squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. And now that's going to let me integrate it like this. So pi over 4 is just pi over 4 minus the integral from 0 to 1. X squared plus 1 over x squared plus 1, that's just 1, right? That's just 1. And then minus, that's still just that, 1 over x squared plus 1 dx. Okay. Okay, so now let's go ahead and split this up into two integrals. So maybe I could have done that in this step, but let's do that here. So pi over 4 minus the integral from 0 to 1 of 1 dx. Then what I have here is minus minus. So if I split this guy up into two integrals, it's going to be the integral from 0 to 1 of 1 dx minus the integral of this guy dx from 0 to 1. But I'm subtracting the whole thing, so minus minus becomes plus. So what I really have is plus the integral from 0 to 1 of 1 over x squared plus 1 dx. Okay. Okay, so I'm obviously completely out of room over here, so I'm going to come back up to the top and make some room up here. So what can we get rid of? Let's get rid of some of this. Really don't want to get rid of much of anything here, but no choice. Okay, so let's continue. Let's use a different color because the green's kind of fading. So what we ended up with was pi over 4 minus the integral from 0 to 1 of 1 dx, and then we had plus the integral from 0 to 1 of 1 over x squared plus 1 dx. Okay. So now these are easier to integrate, right? So pi over 4 minus, if we integrate 1, we just get x. And remember, we're evaluating that from 0 to 1. Okay. And then plus, if we integrate 1 over x squared plus 1, that's just the arctangent, right? So want to keep that formula in mind for sure. So that's the arctangent of x, and we're evaluating from 0 to 1. Okay. So this is pi over 4 minus, so let's think of this as having brackets on it, so minus 1 minus 0. Okay, evaluate at the top minus evaluate at the bottom, so top and bottom. And then plus arctan of 1 minus arctan of 0. Okay. And we've talked about this before, so arctan of 1 is pi over 4, arctan of 0 is 0. So if we come up here, this is this pi over 4, okay, we have this pi over 4 right here. So this is pi over 4 minus 1, okay, and then plus another pi over 4 from the arctan of 1, and then arctan of 0 is just 0, so minus 0. Okay. Now we simplify that, pi over 4, blah, 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 plus pi over 4, so that's 2 pi over 4, which means pi over 2, and then minus 1. Okay. So that's our answer. Okay, so if that seemed kind of convoluted and messy, it really wasn't that bad. There's just some subtle tricks to keep in mind. Okay, so this is our answer here, pi over 2 minus 1. And again, we started with this, but what we said was, oh hey, that's an even function, because it's two odd functions multiplied together, and I'm integrating from negative number to positive that same number. So I can use that property of integrating even functions over intervals like this, and I can say, okay, that's the same thing as 2 times the integral from 0 to that number of that function. Okay, and then we used this Liate or whatever rule to choose u to be the inverse trig function, because that appears above algebraic. So u is the arctan of x, then dv is everything left over. So since it's dv, I tossed in the 2 there, so dv is 2x dx. So then v is just x squared, so that's nice. But again, there are a few different ways to approach this problem, and the way we approach it in this, the way we did in this example here, just kind of simplifies the work a little bit. So if you don't know this property, you would do it exactly the same way, but you would be evaluating integrals from -1 to 1 instead, and you'd have fractions of 1/2 appearing in a few places. So it'd be exactly the same, just the algebra would be just a tiny bit more complicated. It really wouldn't be that bad. You'd have to evaluate arctan of -1, which is -π/4, so you'd have that, but that's no big deal. But anyway, there's that. And also there's this trick we talked about here. So things like this is actually kind of a common trick in math. If you want to integrate something like x squared divided by x squared plus 1, well, since you have x squared plus 1 on the bottom and just x squared on top, then what we do is add 1 and subtract 1. So then we split this up into two fractions here. So this fraction and then this fraction. So that's what we did. We said x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. So that's kind of another tricky part to this. But if you don't like that, or if you wouldn't think to do that, you could just do polynomial long division, which is kind of a headache. But you could do that, and you would still end up with the same thing. If you did polynomial long division on x squared divided by x squared plus 1, you'd still end up with the same thing here. So it'd still work out. Okay, you just have to be careful with that. You know, it's a pre-calculus thing. It's kind of messy, polynomial long division. So you could do it like that, or just think of this trick here. Okay, add 1, subtract 1. So you're just adding 0 in a way that's useful to you. Okay, so adding 0 and multiplying by 1, those are common tricks in math, right? So those are just common tricks to keep in mind. So add 0 in a way that's useful to you, or multiply by 1 in a way that's useful. So we've done a few other things in other videos where we've done stuff like that. But anyway, just keep stuff like that in mind. So this one seems like it had a few tricks to it, but really we just used some properties and techniques to keep things simple. But there are other ways to approach this, which would make it just a tiny bit more complicated with the math, or with the algebra really. But the math behind it is exactly the same. Use this rule to choose u, and then just integrate based on that. And then you'll end up with π/2 minus 1. So that's example 5 with integration by parts with a definite integral.